Okay, having a look at our calendar. Today is November 8th. Today we're going to talk about something called related rates, and I will point out that 2 classes from now we are going to do even more related rates. So 2 sections, 2 days on this topic right here. The quiz is still kind of far away, but while the calendar's up, I want to point out 2 things. Number 1, although today is a Wednesday, GCC considers it a Friday, so you go to your Friday classes today. Doesn't affect us, but it might affect some of you. Does anybody have a Wednesday night class? Go to that class tonight. So it's a Friday during the day, but it's a Wednesday at night. So go to that class. Also, this coming Friday, there are no classes at GCC in honor of Veterans Day. So the next time we meet will be Monday. Okay. All right. So let's take a look. I'll put them out in the, thank you. Today we learn how to solve problems where several variables are changing at the same time. These kinds of problems are called related rates problems. So here's our one demo. It says water is flowing into a cone, and it says the height of the cone is 16 centimeters and the radius at the top is 4 centimeters, and the water is flowing in at 2 cubic centimeters per minute. And then we want to know how fast the water level is rising when the water is 5 centimeters deep, and 10 centimeters deep, and 15 centimeters deep. So let's draw a picture here. So we're going to get our cone. And we're going to go ahead and mark the dimensions here. So it said the height was 16, that's all together. And then the radius at the top is 4. So here to here. And then we're going to put some water in this thing. So I'm going to say the sort of generic water level is there. You just put it someplace in the middle. And so let's test our intuition before we do any calculus. So we're pouring water in at a constant rate, 2 cubic centimeters per minute. The height of the water is changing because the water is filling this cone up. The question is the rate at which the height changing constant, like it just goes up at the same steady rate the whole time, or does it go up slowly and then faster and faster and faster, or does it go fast in the beginning and then slower and slower at the end? Yeah, it's going to be fast in the beginning because there's just not that much space down here for the water to fill. But then as the cone opens up, it takes the water longer to grow, like vertically, right? So that's what our intuition says. We're going to find some actual specific numbers at 5, 10, and 15 centimeters deep. Okay, so let's say that we are going to call the cubic centimeters the volume changing. So we'll call our generic height H, and let's go ahead and call our generic radius down here R, okay? So it is a big cone, but the water itself is also a cone, right? And so those are the labels for the cone of water. All right, so what we're interested in here is the volume, because we're told that the water is coming in at 2 cubic centimeters per minute. Clearly that's a volume kind of number. So we need the formula for the volume of a cone. Anybody happen to have this one? So what if it were a cylinder? Pi r squared h is the formula for a cylinder, right? That one makes sense, right? Because pi r squared is the area of one circle, and you're stacking H circles. Stephanie? It's 1/3 of that. Yeah, it turns out that the cone volume is 1/3 of the corresponding cylinder volume. Okay, so there's our formula right there. And let's also denote this 2 cubic centimeters per minute with some symbols. 2 cubic centimeters per minute. All right, let me see. The cubic centimeters, that's definitely a volume, right? And minute is a time. Would you guys buy that 2 cubic centimeters per minute is a dV dt? It's the rate at which the volume is changing as time passes. dV dt equals 2. Yeah. Oh, yeah. One of those. I got more stuff for you. Hang on. Got this one, and then finally this one. Welcome. Okay, So we've got the dv dt here. So I guess what I'm inclined to do then is take a derivative of this equation in black, where time is the variable. So when I take a derivative of the left-hand side, I will get dv dt. That's information I have, so it seems natural to take a derivative. And when you take a derivative of h, you're going to get dh dt, which is what the question is asking us about. So let's mark that one too. So where did it go? It says, how fast is the water level rising? This is a dh dt equals what we're after. So taking a derivative of that equation is a very natural thing for us to do. And it's totally fine to take a derivative in its current form. However, R is changing, right? As the water level rises, the radius of the cone of water changes. H is also changing, which means R and H are both variables, which means what rule to take the derivative? What rule to take a derivative here? Product rule. It's okay, it's not the worst rule in the world, but we'd have to use the product rule. And in taking the derivative of the R squared term, okay, so it's 2R, but R is changing. R itself depends on time. And so it's not only 2R, it's 2R times the derivative of R with respect to t. So don't write this because we're not going to go this route. But it's 2R times the R dt. The implicit differentiation stuff that we did last class is showing up right here. Right? You do your normal derivative, R squared normally just becomes 2R, but then times, okay, it was like a dy dx last class, but now it's dr dt. And so when I take a derivative of that equation in black, I'm going to have a dr dt in it, which I don't know what the rate at which the radius is changing is, and it's not asking me to find it, and so it's just problematic, right? I don't know it, and I don't want it. And so we're going to go another option here. Let's take a look at the symmetry, I guess, of this picture right here. You've got the small cone of water and the giant cone that's the, the cup itself. And for the giant cone, the height is 4 times the radius. Yes? Just 16 to 4. Would you buy that the height of the cone of water is 4 times the radius of the cone of water? It's the same, like it's a similar cone of water to the original big cone. And so that 4-to-1 ratio has to carry for our water. And so let's write that as a ratio. We know that the height of the water to the radius of the water has to be the same thing as 16 to 4. The height of the original entire cone to the radius of the big cone. And I said that the two cones were similar, and that's right, but really it's similar triangles that I'm after here. Like you guys have some experience with similar triangles back in your high school geometry class, and so that's what we're writing down here, is that it's a consistent ratio for the two similar triangles. Okay, now we've got to think carefully. I want to solve this equation for either R or H and substitute into my volume equation. Given that I really want to know dH dt, I'd like H to still be in my volume equation, which means I want to get rid of R, which means I'm going to solve that equation for R and substitute. So solving this equation for R, I'll cross multiply first. 16R equals, 16R equals 4H. And then divide by 16. And so we get the radius as 1/4 of the height. Okay, so that is the thing we will substitute into our original volume equation. So this guy now becomes V equals 1/3 pi, and then I'm going to put something blank there, squared, times H. So I've left that blank where the R used to be. What are we putting for R? 1/4 H. So that goes right inside the parentheses. Okay, so I like this equation much better because the only variables here are V and H, and I know some stuff about V up on the top there. It says dV dt, and I want information about H. So this equation is good for us. You could take a derivative right now. You'd still be using the product rule. It's not wrong, but it would be better for us to clean this up a little bit before we dive into our derivative. So let's go ahead and square what's in the parentheses. So we get V equals 1/3 pi. And then when I square what's in the parentheses, I think I get 1/16 h squared. Is that okay? Just squaring the 1/4 and the h. And now we can just multiply everything through the parentheses here. So I'm going to group the pi and the 3 and the 16 together. 3 times 16 on the bottom, that's a 48. So that's all my constant multipliers in the front. And then h to what power? H to the 3rd, right? H squared times h. No, all good. Okay, so this is as good as it gets. We've done the pre-calculus, simplifying as far as we can, and now we're going to take a derivative. All right, so we are taking a derivative of both sides of this equation where the independent variable is time. It's not volume, it's not height, it's not radius, it's time. Time is the thing that is changing all of these variables. So when I take a derivative of v, well, normally it would just be 1, right? Derivative of v would be 1, but then times dv dt, right? Derivative of v with respect to time is just symbolized that way. Pi over 48, stay or copy. Sorry, those are the same thing. Stay or go. Pi over 48 stays because it's a constant multiplier times, now what's the normal derivative of h cubed? 3h squared. But h itself depends on time. And so implicit differentiation says times the derivative of the stuff, which is a dh dt. So this is why we do the implicit differentiation section at all. Like we have to do the implicit stuff before we do today so that we can do today. And related rates problems are just much more interesting than any implicit stuff from the other day. So really, like implicit is not, it's not entirely useful on its own. It's useful because it pops up in other circumstances. Okay, so this question asked us to find the HDT because it said how fast is the water level rising. All right, so I think we can just do a little bit of algebra here to solve for dHdt. Equals, oh, one thing, we can clean this up just a tiny bit. 3 goes into 48 16 times. Okay, so dHdt, we're going to divide both sides by the pi and the h squared, and we're going to multiply by the 16. So I think I get this, 16 over pi, where's the h squared going down here? Pi h squared times dv dt. I think I've got it. So divide by pi h squared, multiply by 16. Okay, and we know what dv dt is. It was given to us. How fast was the water coming into the cone? It was 2 cubic centimeters per minute. So we'll just substitute right there. dHdt equals 16 over pi h squared times 2. So 32 over pi h squared. So that right there is our formula. Put the dHdt here. And now finally we get to plug in those values of h that we were interested in. It said when the water is 5 centimeters deep and 10 centimeters deep and 15 centimeters deep. And so one at a time, we're just going to plug them into this thing. So we can just make a little table here at the bottom. Okay, so we've got h, and then we've got dHdt. I'm going to ask my calculator folks to help me out here. So somebody plug 5 into that formula, somebody plug 10, and somebody plug 15. Anybody have any of them? Can you get me a decimal? How much? 0.4 for 5? For which one? Anybody have 10 or 15? Okay, anybody have 15? 0.04. That doesn't feel small enough relative to the 0.102. Okay. That's good. Can somebody double check the 0.102? Maybe it's okay. All right, so let's assume that all these calculations are right. What are the units for dH/dt? Units for dH/dt. Yep, centimeters over minutes. Yeah. So these numbers that we filled in our bottom row, the units are centimeters per minute. So when the height is 5, the water level is increasing by 0.4 centimeters per minute, increasing because that's a positive 0.4. But when the water level is 10 centimeters, it's only increasing by 0.102. Yeah. Not for dH/dt. The volume is changing by cubic centimeters per minute, but the height is just a one-dimensional thing, and it is changing centimeters per minute. And when the cone has 15 centimeters of water in it, now the water level is only rising by 0.045 centimeters per minute, which jives with what we expected. We thought it would rise quickly in the beginning and then slow down as time passed. Okay. All right. So the basic idea for solving these related rates questions is written on a reference sheet earlier in this packet. Let's go back. I think it's page 3. So let's see if you can come right here to page 3. So so this reference sheet talks about related rates problems. There's one example over there about a ladder sliding down a wall. We're not going to read it right now, but I just want to highlight that we do have typed out here like the general guidelines for related rates questions. So you read the problem, make sure you understand exactly what's really being given and what is being asked for. You carefully define your variables. In our case, we had h was our height and r was our radius. It says that some of the values in the problem will be changing. It says be clear on which quantities can change and which stay the same. Now, in our problem, the dV/dt was constantly 2 cubic centimeters per minute. And it said that the height is 5, 10, and 15, but you cannot substitute 5, 10, and 15 in the beginning of the problem because as soon as you make h equal 10, you are stopping the problem, right? Like you are not allowing any more water to come in. So even though at some point h was 10, it wasn't in the beginning. It was only at the very end. Okay, so you draw your picture, keep things generic. We had h and r. We didn't put a 10 in our picture. Figure out what you are trying to find and what you are given. We were given the dV/dt. We wrote that in symbols, and we wanted to know the dH/dt, and we wrote a question mark next to those symbols. And then you got to pull an equation out of a hat that relates your variables to each other. In our case, it was the formula for the volume of a cone, but we had to pull that out of a hat. In other cases, it's a Pythagorean theorem kind of thing. Then you differentiate implicitly with respect to the appropriate independent variable, which is almost always time. In this problem, we haven't looked at it, but dx/dt, dy/dt. In our problem, dv/dt, dh/dt. And then only after you've done your derivative do you get to actually plug in specific values for the variables. And then you solve for the thing you want. Okay? All right, so that's our general process. So what you are going to do now is lots of practice. And so I will read the instructions here for the activity. Just like the other day, the activity here is going to be your homework assignments. You're going to get a bunch of your homework assignment done right now. It's the following problems. These are written on the top of page 12 as well, plus one problem from your textbook. I will point out this assignment is not due until the start of class number 30. Remember I said we're doing 2 days on related rates? So this assignment isn't going to be collected until the class after the other class on related rates. So since we're not collecting it until class 30 on your blank piece of paper where you do your homework and you're not going to be able to squeeze it in the packet, call it homework 29. Okay, so I think that's good. Let's see how far we can get. I want you to do just those specific ones there.